Black holes, the enigmatic cosmic objects predicted by Einstein's theory of general relativity, are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They are characterized by their mass, angular momentum, and electric charge. Remarkably, studies in the 1970s revealed that black holes also possess entropy. Entropy, in thermodynamics, is a measure of the disorder or randomness of a system. The fact that black holes have entropy is puzzling. Classical physics suggests that black holes are simple objects completely determined by their mass, angular momentum, and charge. This no-hair theorem implies that black holes should have zero entropy. However, the work of Jacob Bekenstein and Stephen Hawking showed that black holes do have entropy, proportional to the area of their event horizon, the point of no return. This discovery, known as the Bekenstein-Hawking entropy formula, was a profound insight. It suggested a deep connection between gravity, thermodynamics, and quantum mechanics. However, it also raised a fundamental question: what are the microscopic degrees of freedom responsible for black hole entropy? Traditional physics offered no answer. String theory, a promising candidate for a unified theory of all fundamental forces, offers a potential resolution to the black hole entropy puzzle. Instead of point-like particles, string theory posits that the fundamental constituents of the universe are tiny, one-dimensional objects called strings. These strings vibrate at different frequencies, much like the strings of a musical instrument, and these vibrations determine the properties of the particles we observe. One of the remarkable features of string theory is that it naturally incorporates gravity. In the low-energy limit, string theory reproduces Einstein's theory of general relativity, providing a framework for understanding gravity at the quantum level. Moreover, string theory predicts the existence of extra-spatial dimensions, curled up and hidden from our perception at everyday energy scales. These extra dimensions, along with the extended nature of strings, play a crucial role in the string theory explanation of black hole entropy. They provide the necessary degrees of freedom to account for the entropy of black holes. In particular, string theory predicts the existence of higher dimensional objects called D-branes, which turn out to be instrumental in understanding black hole microstates. D-branes are extended objects in string theory on which open strings can end. They are dynamical objects with their own tension and charge. D-branes can have different dimensionalities, ranging from zero-dimensional D0 branes, which are point-like, to nine-dimensional D9 branes, which fill all of space. What makes D-branes particularly relevant for black hole physics is that they can carry the same charges as black holes. For example, a stack of coincident D-branes can carry mass and electric charge just like a charged black hole. Moreover, the interactions of D-branes are governed by the rules of quantum mechanics, allowing for a microscopic description of their states. In the context of black hole entropy, the key idea is that certain configurations of D-branes, when viewed from a distance, are indistinguishable from black holes. As the strength of string interactions, controlled by a parameter called the string coupling, is increased, these D-brane configurations undergo a transition and form a black hole. Not all D-brane configurations are suitable for describing black holes. To ensure that the D-brane system has the right properties to form a black hole, we need to consider special configurations called BPS states. BPS states are configurations that preserve some amount of supersymmetry. Supersymmetry is a hypothetical symmetry of nature that relates bosons, particles with integer spin, to fermions, particles with half-integer spin. While there is no direct experimental evidence for supersymmetry yet, it is a key ingredient in many theoretical frameworks, including string theory. BPS states are important because their properties, such as their mass and charge, are protected by supersymmetry and do not change as the string coupling is varied. This ensures that certain observables remain constant during the transition from a D-brane configuration to a black hole, providing a crucial link between the two descriptions. Section 5D1D5 branes, a microscopic model for black holes. A particularly well-studied example of a D-brane system that can be used to model black holes is the D1D5 system. This system consists of a collection of D1 branes, which are one-dimensional strings, wrapped around a compact spatial direction, along with a collection of D5 branes wrapped around the same direction and 4 additional compact directions. This configuration gives rise to a black hole in 5-dimensional spacetime. The mass and charge of the black hole are determined by the number of D1 branes and D5 branes, respectively. Furthermore, the D1-D5 system is a BPS state, meaning that its properties are protected by supersymmetry. The advantage of using the D1-D5 system is that it provides a concrete and tractable model for studying black hole entropy. The microscopic degrees of freedom of the D1-D5 system are the open strings that end on the D branes. These open strings can vibrate in different modes, giving rise to a vast number of quantum states. Section 6. The Witten Index, counting the microscopic states. To compute the entropy of the D1-D5 black hole, we need to count the number of microscopic states of the D1-D5 system. This counting is a challenging task, but it can be done using sophisticated techniques from quantum field theory and string theory. One approach is to use a mathematical tool called the Witten Index. The Witten Index is a topological invariant, meaning that it does not change under smooth deformations of the system. In the context of the D1-D5 system, the Witten Index counts the difference between the number of bosonic and fermionic states. Remarkably, the Witten Index for the D1-D5 system can be computed explicitly and is found to be non-zero. This implies that the D1-D5 system has a large number of microscopic states, even at zero temperature. This is in stark contrast to classical physics, where the entropy of a system at zero temperature is always zero. Section 7. Agreement and discrepancies. Comparing with Bekenstein-Hawking. The entropy of the D1-D5 black hole can be calculated from the Witten Index by using statistical mechanics. The result is a formula that expresses the entropy in terms of the number of D1 branes and D5 branes. Astonishingly, this formula precisely agrees with the Bekenstein-Hawking entropy formula for a black hole with the same mass and charge as the D1-D5 black hole. This agreement is a remarkable triumph for string theory, providing strong evidence that it can correctly account for the microscopic degrees of freedom of black holes. However, it is important to note that the agreement between the string theory calculation and the Bekenstein-Hawking formula is not always perfect. There are subtle discrepancies that arise in certain cases, particularly for black holes with angular momentum or in higher dimensions. These discrepancies are an active area of research and may hold clues for further refining our understanding of black holes and quantum gravity. Section 8. Beyond entropy. Implications for quantum gravity. The string theory explanation of black hole entropy has profound implications for our understanding of quantum gravity. It suggests that the information about the quantum state of a black hole is not lost but is encoded in the microscopic degrees of freedom of the D-brane system. This resolves the long-standing black hole information paradox, which questioned whether information is lost when objects fall into a black hole. Moreover, the success of string theory in explaining black hole entropy provides a concrete example of how a theory of quantum gravity can address fundamental questions about the nature of space, time, and information. It offers a glimpse into the quantum nature of gravity and the intricate interplay between gravity, thermodynamics, and quantum mechanics. The insights gained from studying black holes in string theory may also have implications for other areas of physics, such as cosmology and condensed matter physics. For example, the ADS-CFT correspondence, a duality between string theory in certain spacetimes and conformal field theories, has provided deep connections between these seemingly disparate areas of physics. Section 9. Conclusion. A glimpse into the quantum universe. The string theory explanation of black hole entropy is a remarkable achievement, providing a compelling microscopic picture for the thermodynamic properties of these enigmatic objects. By identifying D-brane configurations as the microscopic constituents of black holes, string theory has resolved the long-standing puzzle of black hole entropy and shed light on the deep connections between gravity, thermodynamics, and quantum mechanics. The success of string theory in this domain offers hope that a complete theory of quantum gravity is within reach, one that will ultimately unravel the mysteries of black holes, the Big Bang, and the fundamental nature of our universe. While many challenges remain, the insights gained from studying black holes in string theory provide a beacon, guiding us towards a deeper understanding of the quantum universe.